Uh, L2VPN. Today, just before we start, just want to tell you that keep the session as interactive as possible. We would, and if some discussion needs to be taken or somebody wants to have an offline discussion, Syed Nawaz and I will be there after the tutorial, and we'll be more than happy to assist you with anything. And so, just to give you a little background, what are we going to talk about? Even though the agenda looks pretty long, don't be scared about that. We'll try to make it as simple as possible. We'll walk through basically introduction to L2VPNs, signaling concepts, virtual private wire service transport, that is basically point-to-point. VPWS service interworking, that is if you're talking about heterogeneous environment. Then we'll talk about a very well-known term, VPLS, virtual private LAN service. And then we will be talking about pseudo-wire stitching, quality of service, OAMs, operation administration management, and then Q&A, we will keep it as we go. Otherwise, you want to do it at the end, we can do it at the end. One other thing is we'll be doing demonstrations. We'll showing you the basic functionalities through the routers, and that we'll be doing after every section. Okay, before we start, just want to get your feeling of it. How many guys have you heard about L2VPN here in this room? Good, excellent. Okay, how many of you guys are working on L2VPN right now? Great. So I think so you know the challenges what are there. So let's start with the introduction of L2VPNs. Okay, today we have different access technologies as we talk about. We have IP networks, IPsec, or we have L3VPN. We have FR, frame relay, and ATM broadband networks. We also have Ethernet network. All this because the networks have grown tremendously, and we have different sets of network running across. Some people are using ATM networks, layer 2 networks for their voice networks, and they also have packet network at the same time. How the challenge is, in this era right now, how to consolidate this network. And one of the solutions is provided by L2VPN. So direct access, so in this thing, what we are trying to show in this figure is we have different core. We have MPLS IP core for IP networks. We have ATM core for FR ATM broadband networks. And we have SONET core for Ethernet network. How do we consolidate them? Using MPLS or IP, and using L2VPN as our solution. So L2VPN, as we speak, right, we have heard about routers working on layer 3 all the time. But what is the beauty of L2VPN it brings into the picture is, it enables routers to do the packet switching based on layer 2. So it's working as a layer 2 device. So your router can work as a layer 2 as well as layer 3. And that provides the functionality of basically consolidating the legacy networks of layer 2 devices. So what should be a simplest definition of L2VPN from the picture we just talked about? It provides the end-to-end layer 2 connection. For example, there are two cities, San Jose and Dallas, over a service provider MPLS core. It can be an MPLS core, and it can be an IP core. In case of MPLS, we'll be talking about LDP in detail later. And we're talking about IP, it's basically LDTP v3. So in the figure, if you can see that, so if you have a CE1, I have a CE2. I have L2VPN MPLS IP core there, and I have shown the ingress traffic in cap. So at the ingress side, you can have an ATM interface, or you can have a frame relay interface, you can have an Ethernet interface, you can have a VLAN interface, you can have a PPP or HDLC. So you can talk to different in caps. So there's a whole lot of variety you can use there at the basically ingress side. So, and as we'll talk about in detail, it can be a point-to-point. When I say point-to-point, I mean PE1 has a direct relationship with PE2. And when I say multi-point, then I can say that PE1 is talking to PE2, as well as if there is another PE called PE3, it will be talking at the same time. That's a multi-point network. And that we'll be talking about later in context of VPLS. It's basically, since it says L2VPN, it says layer 2 VPN, so we'll be doing a packet lookup not based on IP. We'll be doing packet lookup based on Ethernet, basically layer 2 header. It can be Ethernet, it can be FR, it can be VLAN, it can be ATM, VPI, VCI. just like an ATM switch. And between the CE1 and CE2, it will appear that is a single wire between a CE1 and CE2. That's why it's called a pseudo wire. So if on CE1, CE1 router sees CE2 as next hop. So just to elaborate more, for example, if CE1 is on a, and CE1 and CE2 has to be on the same subnet. So that's basically the beauty of L2VPN is. And one of the things which basically makes it an exciting technology is there's no routing involved in the MPLS core. And the best thing which many service providers and enterprise are using L2VPN is you don't have to store the route on your MPLS, your service provider network. All your routes control are basically with any customer, whatever who is doing it. So all your routes are either there in CE1 or CE2. No routes are there in PE1 and PE2. So that's basically take a lot of relief to the service provider. So why is L2VPN needed? As we have discussed in the beginning slides also and later also, what is the main motivation behind the L2VPN? What makes it so exciting? Number one, it provides your migration path. For example, if you have existing lot of legacy layer 2 networks and ATM, FR, and you want to move to packet network, you can do a gradual migration. You don't have to change everything in one day. That's basically what migration is. And provision is incremental, like you can do it, like you can gradually move to the packet network, or network consolidation. For example, you want to keep your legacy network at the same time because you have done a huge investment on that part. So you have voice traffic running on your ATM network, you have packet network, so you can consolidate them using MPLS IP core. So your router can talk to a layer 2 device as well as can talk to a layer 3 device. And one of the most important things which brings into consolidation and migration, all those things, you have reduced capital expenditure and your operation expenditures. That is basically one of the key factors which many people basically want to go to L2VPN. So as I talked on the previous slide, the customers in this case can have their own routing, own QoS policies, and security mechanism. They don't have to rely on the service provider. It's an open architecture, IETF, PWE3 draft, pseudo-wire, emulation, H2H. I'll be mentioning the drafts later in my slides. Basically, and the RFCs are there drafts are there, number of smart people are working on it, so there's a lot of improvement and a lot of work is going on in IETF. So one other thing which basically when you talk about L2VPN, many people think like, why L2VPN, why not L3VPN? Is L2VPN going to replace L3VPN? No, it's not like that. So as I go along the slide, I will tell you that Layer 2 VPN is not there to replace L3 VPN. It's going to be there, the RFC 2547 is just basically the requirements, what you have. Based on that, you need to use both the services. Layer 3 VPN is based on, so if you see a high-level difference between a Layer 3 VPN and L2 VPN, in Layer 3 VPN, we're talking about a packet network. So we'll do forwarding based on IP. In L2 VPN, we'll do forwarding based on your Layer 2 header, that is DELC, VLAN, VPI, VCI. Service provider is involved, definitely in case of Layer 3 VPN. In case of Layer 2 VPNs, SP involvement is minimal. Only provisioning will be done by SP, rest of the thing you need to take care of. And that is one of the good thing about it. Is IP specific? In L2 VPN, you have multi-protocol specific. For example, your CE1 and CE2 can run IPv6, can run IPX, whatever, your legacy network, and it will support that. Example, basically RFC 2547 defines the L3 VPN, and in case of L2 VPN, we have put PWE3 drafts. So the disclaimer is the choice of L2 VPN, the bottom says, the choice will depend on how much control the enterprise want to retain. L2 VPN services are complementary to L3 VPN. So so the one thing is very clear, L3 VPN and L2 VPN both will coexist at the same time. It's just based on the requirement, what you want to do and what your requirements are, that you have to use L2 VPN. Any questions till that point, or?
Why distinguish this from the user's point of view? This looks like a multi-port bridge,
yes,
with a very long delay between ports. So as far as the user is concerned, this is just a bridge network, right?
Yes. In case of multi-point, it will be a bridge network.
So why distinguish as a separate service?
Sorry?
What's the benefit of discussing this as anything different than just a bridge network?
In a bridge, basically, right now, yes. So the question is, what is the difference between, it's just acting as as a bridge network. What is the difference between this as a normal bridge network you're talking about, right? So normal bridge network, you have to use a bridging there. In case if you're, for example, a router doesn't support even bridging, you can use that. So that's one of the advantages it brings to the table. So your router or your device or whatever you're using, has to be an Ethernet switch. It can be a router and doing the same job. So basically, it's the capability you're bringing a router. That's what the thing is. I hope I've answered your question, or we can take it offline also if you need more discussion on that. L2VPN models. Okay. So there's an MPLS core, there's an IP core. So in MPLS core, these are the terminologies you will be, once you talk about L2VPN, you will hear about VPWS. So what is VPWS? Virtual Private Wire Service. It means point-to-point. Or VPLS. So if you see the branch here, so this one is VPWS, Virtual Private Wire Service, and this is VPLS, Virtual Private LAN Service. So the main difference between these two, VPWS point-to-point, VPLS point-to-multipoint. In case of VPWS, if you go down the tree, you will see like-to-like or any-to-any. When I say like-to-like, I'll go over the details later, but like-to-like means if you have an ATM circuit and you are talking to an ATM circuit, same circuit, like the homogeneous network, that is called like-to-like. And if you're talking about any-to-any, it means ATM, you can talk to frame relay network. So heterogeneous networks. Heterogeneous networks, you can also call them any-to-any interworking. And in case of like-to-like or any-to-any, you can have frame relay, you can have Ethernet, you can have ATM, you can have PPP, you can have HDLC, you can have everything. In case of VPLS, we are mostly talking about Ethernet networks. You can have an IP core. If you don't like MPLS, it's okay. You can use L2TP-v3 and do the basically same thing, whatever you can do with MPLS. So you can still have VPWS services. I haven't seen any drafts as of yet, but VPLS can also be used for the IP core. And at the same time, you can have the frame relay, Ethernet, ATM, PPP, HDLC. So you have a whole lot of choices there, whatever your core looks like. If you're an IP core, you can go with L2TP-v3. If you're an MPLS core, you can go with LDP. It's up to you. The draft defines the standard for both of them. Okay, this is a reference model for pseudo-wire. So this is the diagram is showing is customer sites in green and customer site, and basically two customers. One is in Dallas, one is in San Jose, and you have an MPLS and IP core. So the first thing is AC. Connection between the customer site and the provider edge router. In this case, the SGC is written there, is a PE router. It's called attachment circuit. In this case, I've mentioned AC1. So between CE1 and PE1, the connection is attachment circuit. At the same time, you can see the Dallas connected to the customer side green, shown AC2. So going back to my previous thing, if AC1 and AC2 are same, that is ATM, AC1 ATM, AC2 ATM, then it is called like-to-like. If AC1 and AC2 are different, for example, AC1 is ATM, AC2 is frame relay, we'll call it any-to-any or interworking will be there. What is pseudo-wire? A pseudo-wire is a connection between two provider edge devices which connects two attachment circuits. And in layman term, pseudo-wire means because customer side 1 will see customer side 2 as if they are connected through a single wire. That basically makes it a pseudo-wire. So basically pseudo-wire 1 has a connection between AC1 and AC2. Emulated service. Between the customer side 1 green, AC1, and provider edge router SJC here, in this case, we have a native service. We will extend this native service end to end. So from CE1 to CE2, it looks like a single wire, and that's why we call it as emulated service. So the same example I've shown through or another, you can have another pseudo wire there, you can have multiple pseudo wires running there. So in the core, it will be any packet switching network. So you can use your existing packet switching network, and on top of that, you can provide this service. So one other thing to mention here is, so you have the main components are pseudo wires in the core going through the packet switching networks. You have attachment circuits between the PE1 and your, basically the provider edge router, in this case SGC, to your customer site, and you have immediate service extending there. So if you see the graph, you will see the same model defined there. Fundamental building blocks. How can I provide, what are the fundamental things you will encounter when you are provisioning or when you're providing L2 services? Control connection. As I mentioned there, you can use an MPLS service as well as an IP service. In MPLS, you will use LDP, the Label Distribution Protocol, RFC 3036, you can use that. Or L2TP-v3, if you're not using IP core. Okay, so the last model we saw a core, we saw customer site routers. The transport component, that is a delivery header, it can be an MPLS label or an IP header. We'll show the diagram later once. MPLS label or an IP header is based on your packet switching network. That is just transporting your layer 2 PDU from the PE, in this case, if you see from SGC to Dallas, if I want to transfer a PDU, I will be using a transport component. And that can be an MPLS label or an IP header. I have a tunneling component, that is a VC label or session ID. In case of MPLS, it will be VC label. In case of IP, it can be session ID. VC label is basically identifies a particular pseudo wire. You can have as many pseudo wire as you want through a PSN tunnel. L2 PDU. So your PDU can be Ethernet, frame relay, or HDLC. So in summary, your PDU, for example, let's take Ethernet, will have a VC label in case of MPLS, will have an MPLS label, and have a control word to pass through the PSN cloud to the remote PE router. So in summary, it looks something like this. The picture looks something like this. If you see, starting from the bottom where the layer 2 PDU is written, this line is basically a control word. What is a control word? Control word is a 4-byte entity in case of layer 2 VPN, which is used, has 4 basically major characteristics. Either, if you want to distinguish between an IP packet and a layer 2 packet, we use control word. If you see in the beginning, there's a thing called reserved there. It basically keeps all to 0 so that we can distinguish between IP packet and a layer 2 packet. It is also used for services like frame relay, for like ATM, where frame relay has a back and front bits there, and you want to transport this bits transparently to the remote PE router, control word is used there. Control word also is used basically for sequence numbering, if you want frame ordering, and for length. So these are the main purposes of control word. Control word is required in some cases, and in some cases it's optional. So if you see a layer 2 packet, it will have a layer 2 PDU. It can be Ethernet, it can be frame relay, it can be ATM. On top of that, you will have a VC label, control word, sorry, and then you have a VC label. VC label is just like an MPLS label. It will have an EXP, and it will always be the bottom of stack, and the TTL. And then top of that, it will be tunnel label. Tunnel label, your can be RSVP, LDP, whatever you're using. So you have 3-level encapsulation. And if you are using back-to-back connected, then there will not be any tunnel label. It will just be VC label, control word, and your layer 2 PDU. So packet switching is in the core. It will run through the top label. VC label identifies the pseudo wire. Your VC label is your pseudo wire ID. And optional control carries layer 2 bits and enables sequencing. So in the right side, if you see there, it's written control word in cap and required. CR means cell relay, is one of the types for ATM, in which control word is not required. You can put it, but it's not required. AL5 is required, that's ATM. Ethernet is not required. Frame relay, it is required. HDLC, you don't need it, and PPP, you don't need it. But it's up to the vendor, whoever is providing service, can put the control word, I cannot put the control word. And control word on the 2 PE routers are establishing the connection. They basically agree upon either we want to use this control word or we don't want to use the control word. And that is signaled through your LDP. Any questions till yet, or should I move on? So we talked about the MPLS core, IP core. So this is basically the header looks like. You have a control word, you have an Ethernet PDU, you have a tunneling header, and you have a transport header in case of MPLS. So if you see a tunneling header, basically it's for MPLS core. So you have a 4 byte of MPLS, you have a VC label and tunnel label that I just showed you the last slide. And if you want to go for L2TP-v3, your 4 byte session ID is the one basically which is used as your session ID. Instead of a VC label, you use a session ID there. And that is basically an example of an IP core. So you can have both the flavors you want. So as I have mentioned that ATM, you can use it. This slide just shows you the different versions of L2VPN services you can use in your network. So the last one, if you see, there's basically the VPLS, which is point to multipoint. That basically emulates like a normal Ethernet bridge. A lot of work has been going on IETF. You can go through pseudo-wire emulation edge-to-edge. What is pseudo-wire emulation edge-to-edge? Basically, it's a mechanism that basically emulates the essential attributes of a service like ATM, frame relay, Ethernet. That basically pseudo-wire emulation edge-to-edge is. PWE3, pseudo-wire emulation edge-to-edge. That basically stands for. Requirements detail are PWE3 requirements and PWE3 framework. The RFCs are there. You can have a look at it. And basically, it's developed for MPLS as well as IP. VPWS, as I mentioned there, you can have a L2TP text basically draft for L2TP-v3. For MPLS, you can use a control protocol draft or particular in-cap type. There are several other drafts are there, ARP mediation, interworking, VCCV, OAM. Just search through the IETF and you will find a lot of information there, and L2VPN standards are there. Okay, in case of VPLS, we have 2 versions here. Either you can use the BGP signaling or you can use the LDP signaling. Both the drafts are there. One is the VPLS-LDP, that's in the bottom, or you can use the auto provisioning through the BGP auto discovery. Any questions here? Am I making sense or? All right. Okay. Let's go to the signaling concept. This basically defines how the LDP works and everything. Signaling. So I'm just showing a PE1 router and a PE2 router through a MPLS and IP core. And we have a pseudo wire between PE1 and PE2. Just follow with me the steps and we will walk through. Xconnect is basically whatever provisioning you are using, but in case of a CLI terms, there's a command called Xconnect we use and we enable on the interface. And that basically starts our target hello session with the remote PE2 router. And then PE1 allocates a label for a pseudo wire. And then it sends a label mapping message. So in case of pseudo wire, when it comes to pseudo wire, there are 2 new TLVs, a couple of new TLVs have been added. One is basically for the fact, where VC fact TLV and VC label TLV. In short, it means you have a pseudo wire and a pseudo wire label. So your pseudo wire and pseudo wire label association is basically transported to PE2. Basically, if you want to establish a point-to-point circuit, one of the requirements is you have to have a VC1 and VC2. The VC, basically your pseudo wire ID should be same. And that basically, it talks to the PE2 router, just to tell, hey, here's my pseudo wire 1, and here's my label 100. So at the same time, PE2 will tell, okay, I have a pseudo wire 1 with a label 200, and that's how they establish this negotiation. So PE2 receives the VC fact TLV and VC LV, and that matches with local VC ID, and then it transports the same thing to PE2. So essentially speaking, in summary, I can tell this slide is, main concept, pseudo wire ID and VC label association. And that would basically both the routers exchange with each other through LDP. So what is LDP binding? It is the association of FEC and LSP label created by placing FEC TLV and label TLV in mapping message. I'll show you the TLV in my next slide, how the TLV looks like. Label advertisement messages, label mapping message is basically sent from PE1 to PE2 with a pseudo wire ID and VC label. This is the pseudo wire ID FEC. That is the ID. The number is 128 or 80. If you have the hex stick, it will be 80. If the pseudo decimal is 128. This pseudo wire ID FEC will tell you the pseudo wire TLV, that is 128, pseudo wire type. So INA has described different pseudo wire type there. You have type 1, type 2, type 3, type 4. So pseudo wire type has to match. If you're using a pseudowire type, for example, 1, or pseudowire type, for example, 4, that's basically a tag VLAN. Pseudowire type is basically Ethernet. So you define which type of pseudowire you're talking about. Either it's ATM, frame relay, or stuff like that. Then you provide the pseudowire info len. It can have a group ID, it can have a VC ID. VC ID is basically the number you can define manually, or it can be auto also. So that is basically LDP signaling pseudowire FEC is sent to the PE2 router, and similar thing has been sent by the PE2 router to PE1 in a label mapping message. So this is a label mapping message basically, which is sent to the PE2 router. And one other thing is, in case of the first pseudowire TLV, it also sends the MTU to the remote site. So basically both P1 and P2 negotiate what they want to do, what the pseudowire is, what is the VC label, how do they want to basically set the MTU. Because your MTU on the AC1 to AC2 has to match, otherwise pseudowire will not come up. Or you have some sort of fragmentation is supported in your system. If it's not supported, then AC1 is going to drop the packet. So in summary, pseudowires are exchanged through directed LDP session or targeted LDP session between the PE2 routers, between the P1 and P2 routers. If they are not directly connected, new LDP FACT TLVs to carry VC information, pseudowire ID FEC element type 128, or you can use a generalized ID element that is type 129, where whatever depends is on your provisioning side. So, and these are carried under the label mapping message. And if you want to get into the details of the entire thing, pseudowire ITF PWE3 control protocol draft defines everything. And if somebody wants to have a discussion on that, we can go over the details also, how this thing works. So in our discussion, I have basically touched MPLS pseudowire and L2VPN are point-to-point technologies for the transport of L2 PDU of native or MPLS-enabled IP cores. This summary. MPLS pseudowire use target LDP session to exchange pseudowire labels between participating pairs, while L2VPN uses control messages to negotiate session IDs. MPLS pseudowire and L2VPN can use optional control word to preserve information in transported PDUs. The PDU can be Ethernet, frame relay, ATM, anything. MPLS pseudowire and L2VPN provides interworking with access circuit management protocols to maintain VC status consistency, that is label withdrawal or con. So one of the things which I have not mentioned in my slides is, suppose an error happens, so there's a withdrawal message is also there. For example, your AC1 goes down, your pseudowire goes down, what will happen to the label? So what we'll do is basically we'll release the labels. That mechanism is there in the LDP mapping messages. So you can have setup and maintenance as well as error messages are defined in the LDP mapping messages. So now Syed Nawaz is going to talk about the VPWS transports, and then I'll be talking about the VPLS later. So any questions at this point? So before Syed Nawaz can start the VPWS transports. Okay. So I'll let Nawaz to start.
Good afternoon, folks. Before I start on the VPWS transports, I hope you have understand the control plane, because that is more important, because the next few slides I'm going to talk about is more of the different types of native services. Before I go into the discussion, let's list down the types of native services we have. Ethernet, we have frame relay, we have HDLC, PPP, we have ATM. How many over here are using Ethernet as the native service for L2VPN? Okay, great. Okay, that is the most common service because VPWS or Layer 2 VPN is trying to simulate point-to-point bridge LAN network. So these are the different types of VPWS transports. The first one is Ethernet over MPLS, which has Ethernet as the attachment circuits. The next one is the frame relay over MPLS, followed by ATM, PPP, and HDLC. I'm going to go and discuss in detail each and every one and what are the PDUs which are carried over and what type of thing makes sense here. Okay, before that, feel free to stop me if you have any questions, because as we proceed, we are going to go through the demo, and I would really like to make people to feel that they have a good idea of what's going on, because otherwise the demonstration will not make any sense. Okay, we have a few routers. I hope it works now. let's talk about Ethernet or MPLS transport. In Ethernet, we have two types of frames. One is the tag frame where you have the VLAN header, and the other one is the raw Ethernet frame. So here, the yellow one, which we don't, I don't think it's reading out, that is the VC label or the demultiplexer field, and then followed by the tunnel label, and then the L2 header. This is the L2 PDU. Here we are going to carry our Ethernet frame. So out of the entire Ethernet frame packet, does it really make sense to carry the preamble and the FCS? No, because it can be generated at the other end of PE2. So all we are carrying here is the MAC address followed by the data, Ethernet type, all these fields. The FCS, the preamble, is dropped here at the provider edge PE1 ingress router. So from the arrow mark shows what is carried in the L2 PDU. The same thing goes here. As Varis has mentioned, each pseudo wire is of different type depending on what type of attachment circuits we use. For example, in the LDP signaling message, we have something called VC type field, which defines what kind of pseudo wire you are provisioning. If you are provisioning VLAN, if you are going to carry the VLAN kind of packet, that's VC type 4. That will be signaled across the pseudo wire during the initial provisioning setup. If you are going to carry the Ethernet raw packet, and if you are going to configure port tunneling, then it is of type VC type 5. So VC type 5 is a very popularly used. The reason behind is it can also carry VLAN tag frames, because it doesn't really look into that. It just takes the packets from that particular port, tunnels it across the pseudo wire, and the egress router removes the headers and sends it across the attachment circuit. So you can see that VC type 4 is used for VLAN, and here we are using VC type 5. We also discussed, I think Varis discussed about the control word. In Ethernet, it is optional. It depends on, for example, if two vendors, if we are going to create a pseudo wire between two vendors, one can support control word for Ethernet as well. So that negotiation happens during the initial LDP signaling. Once you have that initial LDP signaling and we decide if you are not going to use the control word, it's okay. If we are going to use, then we just mark all the fields as 0. And if we are going to use the sequencing number, it's fine. But it is an optional field here. There is one more thing which I have written here. The VLAN tag is transmitted unchanged, but may be overwritten. What does that mean? For example, let's assume you have a customer A over here who is using VLAN 4. And there is another customer this side of the room are using VLAN 5. And you are trying to form a emulated point-to-point VLAN service or LAN network. But these two are different LAN networks, right? VLAN 4 and VLAN 5 of different tags. So what you can do is, as soon as the packet reaches this egress router, PE2, you can rewrite the VLAN from 4 to 5. That is possible. Any questions on this? Because this is a very popular, we have received a lot of customer requests on this just to enable this feature, and it is a very popular feature, and it is defined in the draft. It is up to the PE2 router or the egress or the ingress router to negotiate whether you want to do the VLAN rewrite or not. Next, I'm going to talk about frame relay over MPLS. Basically, here we have the attachment circuits, again like-to-like scenario, where both the attachment circuits are configured for frame relay. Here, what we are trying to do here is we are just going to carry this part of the payload. Because if you look at frame relay, it doesn't matter, it doesn't really need to carry the del C header because it's a local. It can be regenerated at the E2, P2 egress. And the control word is required here. One of the reasons for using the control word is to carry the beckon, discard eligibility and control bit over here. You can see that. The draft says use BFDC, some draft says DFBC. Anyway, it is more of you want to carry all these congestion control mechanisms which you have in a local frame relay network all across the pseudo wire, as well as you want to inform the remote end. So it is very important to carry these bits. This information is very valuable for frame relay networks, and you don't want to lose. Since we are emulating a frame relay network from end to end, we need to make sure that all these kind of traffic parameters are carried. The remaining, it's more of the PDU which is carried. This is a RFC 1490 type of frame relay. There is one more which is Cisco proprietary frame relay if people are using it. So which part of the frame relay packet is carried here? How many are using frame relay here as attachment circuits? Good. Okay. So you can see this sequence number field, which is mainly for reordering of packets, or if the packets get delivered in different orders in the pseudo-wire tunnel, you can enable this feature depending on whether vendor supports this feature or not, and use it for ordering of the packets or packet loss or packet duplication. The draft says you can use this field to overcome those kind of limitations. Next, I'm going to talk about ATM or MPLS. Before I go in there, it is more of two different types of ATMs transport we are going to talk about. One is cell relay, which is single cell, which gets, any AL5 packets get chopped into small ATM cells of 53 bytes. You can either carry those 53 byte cells, and that is cell relay or MPLS, or you can carry the entire AL5 SDU. So here we are defining two different types of transports. First, I'm going to talk about cell relay or MPLS, what exactly it is. Cell relay, again, if you look at this part of the packet, it is more of the 48 byte or the 52 byte of the ATM cell. What happened to because ATM cells are of 53 bytes, is it? So I have removed the HEC field because it can be regenerated again. So this 52 bytes is encapsulated and sent across. Here, control word is again optional. It is negotiated during the initial LDP signaling. But the problem here is, in the core, we have an Ethernet MTU of 1500, and you are using 53 byte or 52 byte of data to tunnel it across. Does that make sense? No, because it is inefficiency, because you are carrying each and every single cell across the pseudo wire. That is not the right way to do it. So there is one more method defined where you can pack more than one cell just to increase the efficiency. That is defined as cell packing. So what is cell packing? Why it is important? You are not efficient by using cell relay. So the next one is maximum 28 cells. Let's assume that you have the worst, you are not having a pause where the MTU is 4470. Let's take the worst case, 1500. What is the maximum number of 48 byte cells which can be carried? If you do the calculation, it will come down to 28 cells. So look at this diagram. Here you have the first ATM cell, followed by the next cell, and followed by the next and next, till 28 or more than that. Depending on the MTU size of the core, you can do the cell packing. This is This improves efficiency. You just have to make sure some limitations are there, which is basically packing is controlled by the maximum number of cells and the timer. These are configurable parameters. You are given a knob to adjust these values. So you can set maximum cell packing to 2 to 28, anything, any number, because 1 is almost cell relay. You are not doing anything. And the MCPT timer, the timer which I am talking about here, is more of how much time do you want to wait for all these cells to accumulate before you send it across. Let's say you are receiving an OAM cell. You don't want to wait for other cells just because you want to have higher efficiency. You don't want to do that. So the MCPT timer is again another configurable parameter which helps you how much time do you want to wait before you pack the cells. Control word again here is optional. As we have discussed, for a lot of transport it is negotiated whether you want to use it or not. Any questions on this? Okay. So we have just seen this is how the ATM cell will be. A single cell relay where you just encapsulate one cell without the HEC, 52 byte as I discussed here, 48 plus 4. Here is cell packing. This can go on and on and on until we reach the MTU size of the core. So we need to really, if you want to be efficient in ATM cell relay, we would like to know what is the core MTU. Do you have 1500? Do you have an Ethernet link in the core? Or do you have a POS link? Because 4470, that means you can pack more than 28 cells or till the MTU is reached. The next one is AL5. What we are doing here is more of you just take the entire AL5. We take these cells, we form the AL5 PDU, we send that PDU across the pseudo wire, but here control word is required. The reason why you need control word is because you are going to map the EFCI, CLP and CR bit. Just like frame relay we have seen, these are congestion parameters. How good the traffic is or how good your network holds. So you have to be, you want to carry this information about your network all across. And based on this, you can do a lot of QoS at the edge as well as at the access networks. So you want to carry this information just like in frame relay. So this service also allows transport of other kinds of ATM cells, which are OAM and RM cells. The next one is more of PVP and HDLC, what exactly it is going to get carried. Again, this is more of HDLC and PDU are transported without the checksum because again these are regenerated. The control word is optional again here. It's not required. So let's sort of the boring discussion, let's do some demo here. I'll show you what exactly happens in VPWS. Mainly, I'm going to show you two examples. We have set up a core. This is what the core looks like. Since we have in the lab, we don't have 5 or 6 routers in the middle. So we just have one more router, P router. So we have P and P2 router enabled with MPLS. And these are your two CEs. How many have done VLAN or MPLS provisioning here? Excellent. Okay. So next is for others to go and try it out. So from CE perspective, what do we do here? We are just considering these two CEs are connected back to back. Just assume these two CEs are connected back to back. What will you do? You just configure the IP address, assuming they are in the same network, 192.168.1.2, 1.1, 1.2, and whatever the VLAN. Because here I'm doing, since I have VLAN, I have two options, as I discussed before, VLAN over MPLS and Ethernet. Here I'm going to talk about VLAN over MPLS. These are my PE2. As I said before, the CEs are not aware there is an L2 pseudo wire. But look at the PEs. They are not configured with IP address. What happened to that? Because now they are going to simulate L2VPN. So what is this is a Cisco specific command. Different vendors have different CLIs. I'm just going to go with this. Xconnect, it's basically it says Xconnect the IP address of the remote PE followed by the VC ID. And encapsulation is MPLS because I'm using an MPLS as the core. If you use IP, then encapsulation will be L2TP-v3. The same thing here. The loopback of the remote IP address. This is your VC ID and encapsulation MPLS. So as Varis has discussed about the LDP initial signaling, we are creating a targeted LDP session between PE1 and PE2. These are not connected directly back to back. These are connected through a lot of P routers in the middle. So we are having a directed LDP session between PE1 and PE2. That's why we are providing a loopback address of PE1, PE2 here, and PE1 here. And one of the requirements to configure Xconnect is to have the same VC ID. Here the VC type and VC ID should be the same. VC type, we already know that it is VLAN or MPLS because we are configuring under the VLAN subinterface. And the VC number, VC ID number is the same. VC ID 1 and VC ID 1. If you use 10, it's a random number, you can select. Just make sure that you have the same VC ID at both the ends. Are you guys with me? Everyone clear on this part before I show how the ping and trace out? Okay. So let me show you first the C to C1 to C2 ping. Okay. We have seen here, I'm going to ping from C1, 192.168.1.1. I'm going to ping from C1 to the other end of the loopback address, which is 192.168.1.2. Okay, looks like it works. But ping doesn't prove me that I am connected through the pseudo wire. Let me do the trace route because I might be using different router or route path. Just a one hop. So you can see that it is connected just like these two CEs are. I'm creating a emulated point-to-point LAN network here. They are connected back to back. Right? So let me show you how the control plane or signaling is established between the PE routers. So this is again a Cisco specific command which I'm just showing you. Show MPLS L2 transport, L2VPN, VC, the VC ID which we have used. I'm not sure people are able to see this.
I think you may have to expand it. It's hard to see.
I don't see. Do you see it now? It's very small. Oh, okay. Is it possible for you guys to see these numbers? No? Yes? No? No. Okay.
It's not working.
Okay, looks like there is some other issues there. So what I wanted to show you was the two different labels which are used. One is the atom pseudo-wire label and the tunnel label, just to switch across the core. Okay, I think you guys have to a little bit focus more on this. So I'm sorry about that, but these are the two, there are two numbers which are, I'm just going to read it out, 19 and 28. These are the two labels which we are talking about, which is one label is used for the pseudo-wire tunnel and the other one is just to go through the core. So there is an atom label or the VC label which has been exchanged between the P1 and P2 for that particular pseudo-wire, and there is a tunnel label just to switch across the core. So the next one is pretty much the same, but here we are going to do for cell relay over MPLS. You have the same kind of ATM edges. You can assume that they are connected back to back, and you do the configuration. PVC 0/32 on both the sides and IP addresses. So they are connected 2.1 to 2.2, same network. What do you do in the P2 where the exact configuration for atom tunnel goes? What I have enabled in addition to what I showed before in the previous slide, I do the same thing, L2 transport I added here, the same Xconnect command, but here I'm saying encapsulation AAL0, because here I'm doing a single cell. I'm not doing AL5. So here I'm going to do cell relay over MPLS. So I'm just going to ping from again the CE1 to CE2 through the ATM cell relay or MPLS. .2 is the other end of CE2, so here it is. Same thing can be done for frame relay, PVP, HDLC. And you will see again in the control word in the P2 router or having all the detailed description of how these labels are assigned. The P router doesn't have any knowledge. It is more like a P router of L2VPN. It has no idea what is going on at the edge. The CE routers assume that they are connected back to back. It's all the configuration specific for L2VPN goes in the PE1 router. The provisioning, as you see, it's not as complex as in L3VPN where you have to define tons of things like VPN ID and stuff like that. One more thing I'd like to show here is show SPF neighbor. This is one of the one routing protocol I have enabled between two CE routers, and they see each other as if they are connected directly back to back. So what is the advantage of here? In VPN we have so many limitations like, okay, this is the maximum number of prefix the customer can provide or customer can exchange. Here we don't have any limitations. As in one of the slides, you are giving flexibility to the customers. They can have a BGP peering or OSPF or any routing protocol. And they can send as many routes as they want because they peer directly from one CE to the other. They can form an IBGP relationship or whatever it is. So you don't need to really constrain the customer asking them, okay, this is the limit. You have reached the limit of certain number of prefixes here. You don't need to worry about the aggregation which you are going through in VPN. Here you are just telling them, here is a tunnel, okay, here is a pseudo-wire tunnel. You do whatever you want to. So they have an option of using any IGP they want. Sure.
One of the goals here, I believe, is to emulate bridging, correct? So in that case, are you maintaining a forwarding table and running spanning tree to prevent loops?
So in case of bridging table in point-to-point, you don't maintain a bridging table just because it's point-to-point. In case of VPLS, yes, you have to maintain a MAC forwarding table. And you just like any bridge, you create a table there with learning the source MAC addresses, and based on that you forward it. When spanning tree, it's up to the provider if the box supports it or does not support it. In case of VPLS only. In case of point-to-point, it's point-to-point, so you don't need it much there. But the packets, the spanning tree protocol packet, you can transport it transparently across the core.
Well, the problem becomes if there's parallel links, then you get loops.
Right.
So there's no provision for that.
But in case of multi-point, yes, the problem exists. So you need to basically the way you do it is either you use your box should support it, or your layer 2 switch should be able to have the mechanism there to support it there in case. Or you can transport the spanning tree protocol transparently. In both the cases, yes, you need to take care of that. Does I answer that question or?
Well, then you're not emulating bridge.
In case of point-to-point, it's not a bridge in fact. In VPLS, it's more of a bridge. The point-to-point is one point to one point. You're not learning it much.
I think just one more point I would like to add is here we are saying emulated point-to-point LAN. Point-to-point LAN, the router doesn't get involved in any learning or any forwarding mechanism. If you do right. So in multi-point, the PE router is fully involved as if it is a bridge. Here, if you are using Ethernet port mode, what type of packet the PE router receives has no idea. All it is going to do is take the packet, tunnel it across the pseudo wire, and send it to the other end of the attachment circuit. Okay? So now we have seen the easy way of having two different or two same attachment circuits. Customer A and customer B all are good and great. They are using Ethernet. All are using Ethernet. So like to like, you have the pseudo where everything is good and great. Now we have a different kind of interworking here. For example, customer A is using Ethernet and customer B is using a different native service. Let's say frame relay or VLAN or completely different. What do we do now? So there are drafts which are defined just to do interworking between two different native services here. The attachment circuit one will be supporting frame relay, the other one will be supporting Ethernet. This is how it's going to be in a real life, where you have one end of the customer who wants to maintain their legacy network. They don't want to move to new ones. One side they have frame relay, the other one they are still using Ethernet. Maybe ATM and frame relay, Ethernet and ATM, PVP and frame relay. So all these different types of native services are there. So there are different protocol, drafts which are defined just to do the interworking, where you terminate the protocol at the P, take the layer 3 PDU, or bridge it, depending on what you want to do, and translate it to the other protocol which is on the other side of the P. What are the challenges we have here? For different native services, we have different circuit identifiers. One frame relay uses Del C, ATM uses VPI, VCI, Ethernet uses VLAN or port. The same thing with the traffic parameters, the same thing with the prioritization. For example, frame relay uses different parameters for traffic prioritization. So layer 2 interworking, you have two different services available. One is IP or MPLS. What you do here is you carry whatever type of native service packet from the C to the P. You just take the layer 3 PDU, encapsulate it and send it across the pseudo wire tunnel. The PE2, depending on what type of attachment circuit, it prepends the layer 2 header and sends it across. This is the most simplest form. Obviously there are some other issues like the traffic control, those kind of things needs to be marked. It cannot be done here. And it is very much for IP. So this is called IP interworking. And the other one is Ethernet. Let's assume you have Ethernet services here at this end of the C. And your attachment circuit is also Ethernet. But you have a blue attachment circuit which is different. Maybe ATM, maybe frame relay. But what you want to do is you want to again emulate VPWS kind of service between C over here and the network here. If you do a normal routing on C, your Ethernet end cap is gone. So you have to do bridging here and use an Ethernet or MPLS, which I'm going to discuss in detail. So basically we have two different models which can be used depending on what you want to do. You want to make it very simple, or if you have Ethernet at different native, at the ends, and you want to do bridging. So let me talk about IP interworking here. I'm just taking an example. It doesn't mean just there is a support just for Ethernet to AL5. It can be anything to anything. any to any. Ethernet to AL5, Ethernet to frame relay to VLAN, anything. So here you have ATM, and here you have Ethernet or VLAN, and you have configured IP over MPLS pseudowire, which is of type 11, which is again defined in the VC type draft. What kind of pseudowire you are using. What exactly happens? You are getting a layer 3 PDU in some form, maybe whatever it is, Ethernet frame relay from here to the CE1. The CE1 encapsulates the ATM header and sends it across the attachment circuit towards the PE1. Now the PE1 is configured for IP over MPLS. So what it needs to do is just take the L3 PDU and remove the entire ATM header, because it doesn't care. You have configured an IP or MPLS pseudowire. So what you do is take the IP header, add your labels, your control word, if again it is optional here, your VC label and the tunnel label, and send it across the pseudowire tunnel. Now it is received at the PE2 router. Now the PE2 router is connected to a different kind of native service. And the PDU which you need to transmit is here in the pink section, which is IP. So what you do is you just take the IP PDU after removing all the labels and headers, and once you know which interface you have to send it to, based on the native service, here it is Ethernet, add the headers over there. Ethernet or VLAN or frame relay, whatever the case might be. Here we have Ethernet. So what you are doing is you are just transporting, making sure IP is transported across from one CE to the other CE, from different types of native services. Now the next one is going to be bridge interworking. Why do we do bridge interworking? We have Ethernet here. We have frame relay here. We can do Ethernet to frame relay IP interworking. But we have here, which I'm not showing, it's not showing up in the diagram, from CE1 on this side, we have Ethernet. So we want to have a VPWS kind of a circuit between this network and this red Ethernet. But the problem is we have frame relay circuit here. If you enable normal routing, the CE1 router will remove the Ethernet header and send it. But we don't want that to happen. So what we do here is do bridging at CE1. So CE1 definitely needs to support bridging. So here we are receiving a Ethernet packet towards the CE. We are not stripping off the header because we are doing bridging at CE1. So we are adding the frame relay header on top of the existing L2 PDU and sending it towards the PE1 router. The PE1 router here is configured for Ethernet over MPLS. Nothing special here. You are just configuring an Ethernet over MPLS pseudowire. Same VC type 5, which we have discussed before. So what it does is it just removes the frame relay header and sends the payload. Here the payload starts from MAC header all the way till the L3 PDU. So you see the MAC header with the L3 PDU, and you add your control word, VC label, tunnel label, and send it across the pseudowire. Now once the PE2 receives it, it just works as a normal Ethernet or MPLS pseudowire, where you remove the demultiplexer headers and sends it across the Ethernet. This way you achieve a point-to-point VPWS Ethernet service from this CE all the way over here, irrespective of the fact we have frame relay here. So this is bridge interworking. I hope again, I'm going to show you demo of IP interworking, how exactly it works, what are the configurations required for that. So again, it's just going to be a ping. So what do we do in IP interworking? How difficult is that to provision? Because we said we can do any to any. Frame relay to Ethernet, Ethernet to VLAN, ATM to VLAN, ATM to frame relay, all kinds of things are possible, we said. From CE1, we just configure whatever needs to be configured and assume that CE1 and CE2 are directly connected. And you really don't care about what is the VLAN header and do we need to match. No, you just want you just want CE1 and CE2 to be connected back to back. So here you focus on your subnet 4.1 and here it is 4.2. So same subnet 192.168.4. Here you have a PVC configured at the CE and here you have VLAN configured. Now we have to make sure that the PEs are not configured for normal pseudo wire type because we are doing interworking. Here is what we are going to do. We are going to create a pseudo wire class called NANOG. And what does NANOG has? Pseudo wire class NANOG. Encapsulation again, it's MPLS core, so MPLS. But interworking IP, this is again a Cisco specific, so it might be different for other vendors. So interworking IP, what are the other options? Interworking bridge, right? So interworking IP, over here. The same thing here, it goes here. So I'm just going to ping from an Ethernet pseudo wire C1 to the ATM pseudo wire or ATM attachment circuit, which is 192.168.4.2. So it is going to go from C1 with the Ethernet packet, just take the L3PDU all the way across to C2. And C2 is going to reply back. So I just ping 192.168.4.2, which is ATM interface through an Ethernet using IP or MPLS. It is connected back to back. At least it emulates that it is connected back to back. We don't see a difference. Again, we can have all the advantages of having this kind of back-to-back connection. And we don't really want the customers to move from Ethernet to frame relay or frame relay to VLAN just because we want to do like to like. We don't need to, as long as we know it's going to be IP packets. So I'm just, obviously, I don't think it is visible, but just read out the details. On the PE router, so again here you don't see anything special. Sorry for the font size, but here one thing which is noticed here is interworking type is IP is written here. And the labels remain the same. You have two labels. One is for the pseudo wire and one is for just to send it across the PS antenna. So before we move on to the next topic, are there any questions in interworking or VPWS or even the control plane? So all the pseudo wire types, all these attachment circuits, everything is sent across the LDP signaling which we have this, the initial setup where we do the control plane signaling in the LDP messages. For each of these VCs, we have a pseudo wire type defined. We can also send the optional parameters like what is the MTU at the edges, those kind of things. Any questions so far? Any questions or on the demo or anything else you want to see on the demo? Okay. So the next topic is going to be VPLS. Probably I think we do have time and we can start discussing on the VPLS. I'll come back later for some QS topics and pseudo wire stitching.
So, what exactly when we say multi-point? In a very layman term, you want a universal bridge. A global bridge in fact. A bridge where everybody in the world can connect and they will be connected as if they are connected to a same LAN. That was the whole idea. If you see the picture, a customer route .1, .2, .3, and these are different customer switches and everybody is connected through one core network. They may be globally dispersed or they may be located in the same place. That's what the VPLS brings in. It's a point to multi-point solution, multi-point to multi-point solution, where your router or your device, whatever, is acting like a switch. So, and if you see on the bottom picture, if you see this is a logical view of the diagram that how one user will be seeing the other user in that thing. We have talked about Ethernet point-to-point. We have talked about VLAN point-to-point in our last cases. So what exactly a bridge means? In case of bridge, we have several requirements. In a summary, VPLS, it's an end-to-end architecture that allows IP/MPLS networks to provide layer 2 multi-point Ethernet services while using LDP or BGP as signaling protocol. So, in short, any bridge in the world, what the major functions it can do, it can have the forwarding table, it can support aging of MAC addresses, it can do flooding if it doesn't know the MAC addresses, like any Ethernet switches in the world. It can support spanning tree protocol. So the fundamentals of a bridge, and that fundamentals of a bridge have been moved to a router, and that will follow the same architecture. So essentially, you are emulating an Ethernet bridge in case of VPLS, virtual private LAN switching. Bridge functions, operation is the same, the third bullet is the same for Ethernet bridge. Forward using the destination MAC addresses, LAN source MAC addresses, and floods, broadcast, and unknown addresses. Several drafts exist for VPLS. There's a draft for VPLS for LDP signaling. There's also a draft based on BGP signaling. Each vendor has its own preference to support what. And based on your requirement, you can implement whatever you want to. VPLS components. Very similar, if I give you, if some of you guys have worked on L2VPN, little basic concept of L2VPN. In L2VPN, we have a concept of VRF, virtual route forwarding instance. Similar concepts is there in case of VPLS, that is VSI, virtual switching instances. So in this diagram, you can see a CE router starting from your left to your right. CE router, you have NPE, you have attachment circuit, you have IP/MPLS core with pseudo wires. Then you have remote side on the right side NPE, you have CE router, and you on the bottom you again see a NPE with a CE router. So what is the major difference you see in the diagram now? Now it's no more PE1 and PE2. Now we have another PE router there. Now, the router on the left side, the NPE, that is this one, will have a neighbor relationship with this PE as well as this PE. So now my PE router will be talking to two PEs. So just from a definition perspective, CE stands for Customer Edge Device, used to connect to SP network. NPE means Network Facing Provider Edge Router, that is facing the cloud. VSI, Virtual Forwarding, Virtual Switching Instance, is basically the mechanism by which it will be working as an Ethernet bridge. Pseudowire is, as we have discussed before, the functionality of pseudowire is still going to be there. And pseudowire connects to VSI, consists for a pair of MPLS unidirectional VCs. Attachment circuit between CE and NPE we will call it an attachment circuit. Tunnel LSP is just like any MPLS path and label the tunnel transport label, which will be used to transport the VC, the VC label removed from the remote site. One other thing I want to just point out in this diagram is the red VSI. Red VSI, just as I mentioned before, the concept, if you have guys worked on L2VPN, is a similar concept of a VRF. So red VSI is basically the ID, or just like a pseudowire ID is an ID or VC ID, which basically tells you the particular instance of a bridge. In this case, I've named it as red. So red red on a remote P routers will form a one bridge. You can have several bridging instances in the same router. So VPLS requirement, once we talked about the bridge and everything, so VPLS comes with a requirement, flooding and forwarding, very important concept. In case of a normal Ethernet switch or any bridge in the world, if a packet comes in, it looks for the destination MAC address in your MAC table, right? If the destination MAC address is not there, it will learn the source MAC address and will flood to all the ports. That's what the bridge does. That is we call as flooding. And if there's a traffic from the other side, I'll show you next diagram. And if we have the address, in the MAC table, we will unicast it because I know which port is associated with it. That is the difference between a flooding, forward. The first thing we are doing, we are learning. Then based on the MAC address present or not present, if it's not present, we'll flood. If it's present, we will forward. That is the basic concept between a forwarding and a flooding. Another important thing which a switch would require, but always a bridge in the requires basically, your MAC address should time out, age out. If they're not being used after some time, there should be an aging mechanism which should support that. So we do support self-learned source MAC to port associations. We refresh MAC timers. If the incoming frames are present, the traffic is going, we don't want to age them out. So there's a new also TLV. For MAC TLVs also exist. For example, if your attachment circuit goes down, so your neighbor is no more present, so you need to do a withdrawal of the labels. And you withdraw the MAC address so that the traffic doesn't block black hole in that thing. Loop prevention, a very important concept. Since we're talking about a bridge network, so you can see the issues involved here. Fundamental issue you can see in this one is the broadcast. There's a big issue in the network, so you need to take care of that. Loop prevention, so you need to create a full mesh so that you don't have loop. You can use a split horizon concept there. That is, if you are arriving on one port, don't send to the same port. And that basically are the loop prevention methods. Another loop prevention method is basically you need to rely on your, if you have using your router or your whatever device, it doesn't support split horizon, it doesn't support basically spanning tree protocol, then you need to rely on your layer 2 switches which you are connected there to do the spanning tree for you. So you need to design your network well in this case. So this basically diagram, animation will show the concept of flooding and forwarding because that's a major concept in VPLS. So if you see the diagram, I have a CE routers. I have CE2, NPE1, NPE2, NPE3. So I have 4 routers there in the core and the CE routers are there. So now from left side, a red arrow comes to NPE1. NPE1 will look at the packet and it says, okay, I don't have the destination MAC address. What should I do? I will flood it. When I say flooded, it will flood on all the pseudo wires. Basically, it's all its neighbor. So right now, NPE1 has a neighbor with NPE2, NPE3, NPE4. So I'm going to flood to all my neighbors. That's what any switch would do, right? Now, if you don't want switching, if you don't want flooding, what do you want to do? You start, and basically from NPE3, you send it to NPE1. So that makes it a unicast. Now, the reason why, because initially your destination was the CE router, which was connected to NPE3. And you were sending the packet, but it was going to all the NPE4 also, NPE2 also. Now in this case, when NPE3C starts to send the traffic to NPE1, the NPE1 MAC table will have the source, it will have the address as well as the pseudo-wire association is present there. And once the packet comes to NPE1, it will know that if I have to go to CE connected to NPE3, I need to go through NPE3. So that's how we create a unicast stream. Otherwise, if you don't have a bidirectional traffic, it will always be broadcast. So you need to make sure that this is a very important case of VPLS. You need to take care of your broadcast. That is a fundamental thing you need to do when you are basically creating a VPLS, because that is one of the problems which basically your network can congest, you can have problems there. So it's better to, when you're designing a network, make sure you don't run into broadcast a lot. So that is basically, the diagram is showing that NPE3 is forwarding to the NPE1 with a unicast stream. Some of the characteristics we want to see, since I've mentioned about neighbors, so I'll show you the configuration and how the neighbors are defined. But one other thing is, it's basically good to have is auto discovery of VPN membership. That if I have number of sites connected to each other, I don't want to go and configure manually each and every neighbor. What I want that once a neighbor comes in, it should detect automatically, okay, 4 neighbors are there and everybody comes in with the same VSI ID, it should be able to detect and say, hey, we are all part of the same VSI ID, how about making a one VPN? So there should be mechanisms are there in case from LDP also and from BGP also. So auto discovery of VPN membership. Signaling of connection between PE devices, that is basically the similar signaling we will see in case of the same signaling, the LDP or BGP signaling you can have between the PE routers. Forwarding of frame is basically, again, the same concept is there that we should support unicast, broadcast, and multicast, and the loop prevention as I have discussed in my previous slide. So one of the key concepts in VPLS, just basically I want to go summarize it, that unicast, broadcast, multicast, and when any you buy a VPLS service or look for a software which supports VPLS, look for MAC timers, look for MAC withdrawals, that can it do MAC withdrawal if the circuit goes down, and you find out if basically what are the split, how the loop prevention is happening in that system. But that's basically few things you should look for in a VPLS environment. But the best thing it brings is simple, it's cheap, very easy to provision, and you can have a global switch. That's basically the power of VPLS is. One of the problems, as I mentioned before, because since we are talking about, before I go there, let me ask you a question that does anybody has any concerns at this point or any questions for VPLS? Yeah, please.
Yeah, back on the chart where you had the red VPN.
Yes.
Could you also have a blue VPN if those were VLANs that were the access circuit?
Yes, basically there are 2 types you can define. The 2 types of basically you can say, one is you define per VLAN bridge instance, or group of VLAN can have the same bridge instance. Yes, you can have that. Any more questions? Another one of the important problems which occurs from when people start deploying it, they saw one of the issues is basically scaling. How do we scale it? Since we are talking about full mesh in this scenario, since we want to avoid loops and everything, how do we go about this thing? So there are 2 architectures of VPLS. One is hierarchical and one is non-hierarchical. The non-hierarchical, we call it a single PE. Hierarchical, basically, there are 2 methods of doing hierarchical. Either you can do MPLS access or A22.1D, that is Q and Q. How many of you know what Q and Q is? Q and Q is basically multi-tag packet. The VLAN, if you see a VLAN packet, right, it's 118 bytes. If you just remove the preamble and the FCS. Now, the VLAN header in your .1q packet is only one tag, and Q&Q will have two VLAN headers there. And the reason we do this is very simple. Just like a NATing, just like a NAT we do in IP addresses, the service provider will give you one VLAN tag, and the customer can use this, whatever VLAN tag it wants to, but it will use the same customer service provider tag. So service provider will just look at the tag provided by the top tag, and the bottom tag can be anything. That's basically Q&Q. Q&Q means two VLAN tag packets. So each architecture has its own scaling and different characteristics. Just to mention about the one of the applications of VPLS, what we saw there, many vendors are using. Some of them are using for triple play. That's one of the very famous application where you can transport voice, video data. As I mentioned, it's very cheap, very simple, very easy to implement. And one of the other is implementation of VPLS, which you see a lot, is carrier supporting carrier. I don't know, you guys are, in L2VPN we have a solution called carrier supporting carrier. For example, you have a customer who itself is a carrier, but he wants to transport through a service provider. So it's you have to do a lot of provisioning, you have to do a lot of configurations and everything. VPLS provides a very simple and easy provision way of you can connect multiple customers, and at the same time, these customers control everything, your routing, your QoS and everything, and service provider doesn't involve in anything. So that's one of the beauty of VPLS. So these are the two highlights applications which are in the market, and many people are using it, and based on requirement you can see what is best for you. So how do you want to go and build a VPLS core? So we look at the hierarchy here, the scaling issue. So this is basically a VPLS, the first diagram, without any hierarchy. And the second diagram is HVPLS with Ethernet access. Okay, when I say Ethernet access, what does that mean? It means your PE router is connected to a switch or a layer 2 switch or a router which supports MPLS. So if you see the diagram, the second diagram, there is a UPE written there and there is an NPE written there. So UPE and NPE will have a MPLS pseudo wire there, and in fact that is basically the third one. The second one is basically Q&Q. So let's look at the third one. UPEA and NPE1 has a MPLS there, so that's why it's called MPLS at the edge. What they will have is basically point-to-point pseudo wire between UPE1 and NPE1, and NPE1, NPE2, NPE3 and NPE4, the third diagram. In the core they will have full mesh, and you don't need to create a full mesh at the edges. So that's how you avoid a lot of scaling issues, and that is called MPLS at the edge. In the second diagram, what you can do is your UPE, if you look from the left side, your UPE will have a Q&Q, will be basically taking a packet and doing the aggregation and will be sending it to NPE. So that's how you don't have to go and configure each customer for VPLS. So that's how you do a hierarchical VPLS. So there are two ways. One, the second diagram, HVPLS with Ethernet access is Q&Q, A22.1 AD. And the third one is HVPLS with MPLS to the edge. Both the features are there if you have scaling issues. If you don't have, if you're flat, you can use the flat. You don't need all HVPLS. Just do a provisioning and do whatever you want to. So these are basically the issues which come in when you have a large service provider and you want to deploy VPLS in the core. That's one of the issues comes in. Okay? Any questions? It's a little complex topic to understand, but it's not. It's basically for if you have. It's only for if you're running into issues. If you're not, go for a simple flat topology. That will work for you. So that's basically the next slide is, if you are using a flat, no hierarchy, yes, you can use it. With small implementations, go for it. For simple provisioning, full mesh of directed LB sessions, don't need any Q&Q, nothing. Just VLAN, Ethernet port, connect to each other. They will talk to each other. Drawbacks, if you are scaling and if a lot of pseudo wires are there, then you will learn to hierarchical, then you need a hierarchical VPLS. HVPLS, best for larger scale deployment. Reduction in packet application and signaling overhead on PEs. Full mesh for core tier hub only. Attachment circuit affected through layer 2 tunneling mechanisms. So all these benefits are for the large deployments. Complicated? Yeah, it's complicated. It's one of the drawbacks. But and one other thing is your UPE needs to support MPLS or Q&Q in case to support the HVPLS there. So these are the major highlights between HVPLS hierarchical and non-hierarchical. So I'll just show you, because Nawaz has shown you in the previous demos, the point-to-point relationship. So if you just follow with me the configuration. So in this one, let's look at this box first. This is a PE1 configuration. If you see the configuration on the top, I have written L2 VFI NANOG manual. VFI means the VSI or VFI means the same thing. You just have to give any name. In this case, I put NANOG, you can put NANOG, whatever names you want to. The next line is very important, the VPN ID. That's 100 in this case. It should be globally unique in your network. Bridge domain is 100. It's local to your router in case of Cisco. And I'll explain you what is basically a bridge domain works. Bridge domain in this case is basically identifying a particular bridge in your local router. In this case, it's 100. But the important thing to look for is, look at the neighbor relationship. Now I have two neighbors. That basically makes it point to multi-point. Now I'm talking to two PE routers. And look at the provisioning, it's very simple. You just need to go onto this VLAN and enable bridge domain 100. So bridge domain 100, basically once you put it in there, it points to the basically VPN ID here. It's basically used as a pointer. So put a bridge domain ID, it will refer to VPN ID. That's how they match. That's why you need bridge domain in your configuration. Once you push the bridge domain 100 in your VLAN configuration, and same configuration you will do in all the three routers, in this case PE2 and PE3. Only difference is your neighbor will be changing. In PE1, my neighbors are PE2 and PE3. In PE2, my neighbors are PE1 and PE3. In PE2, my neighbors are PE1 and PE3. And all of them belong to the same VPN ID. Do you see that? Have I lost everybody, or does it make sense? So,
neighbor stuff in
sorry?
every VPN?
Sorry?
We put all this neighbor stuff in for every VPN, or you put it in once for the network and then you build the VPNs on top of them?
You can. So your question is, do you want to have same VPN all of them, or?
Do we have to build this neighbor relationship for every VPN that's defined?
Because you want a point to multi-point relationship, so you need to define the neighbors there. So whoever, that's basically, if you're using auto provisioning, then you don't need to define it. It will done it automatically. But in this case, I'm showing you a manual way of doing it. Okay. So if you see the configuration, if you have a bridge domain 100, all of them, and VPN ID, all of them, they are all part of one big happy family, VPN ID 100. And this bridge is bridge 100. So that's how we make the same bridge domain. So now I'll show you through the routers. Before that, I was able to ping only CE2, as Nawaz has shown you in previous demos. Now I will be able to ping a similar setup. So now I have pinged from CE1 to CE2. And this is, I have pinged to the 3.2, I have pinged to CE2. 3.3, I have pinged to CE3. So now I can ping multiple routers, multiple CE customer routers. That is, and one of the key things to look for here is, so in previous example, Nawaz has shown you the show MPLS L2VC, which was only showing one neighbor. Now, look at this. This is actually very interesting. The first one shows you one neighbor. Let me put the. So this is one neighbor here, and then there's another neighbor. If you see that the VFI is up, VFI named Sena. So it means basically they are part of the same bridge domain. If you see the label stack, right now it's showing only one label because I have put direct connection there between them. There's no core router there. And the VC status is there, interworking type, VC ID. So everything is same as XConnect. The only difference is I'm just establishing one more neighbor. And if you see that, I have two neighbors connected there. So that's what VPLS brings on the table. It basically, so in summary, you define a bridge. Each bridge has a VPN ID. You associate that VPN ID with that particular interfaces. Your VPN ID has to be same on global, whatever your network is. Your bridge domain, your bridge ID can be local. It doesn't matter anything. As long as you're part of the same bridge domain, you can talk to each other. And basically, you will be able to transport whatever. So first, you will do basically you will be having a MAC table, just like a switch. Let me show you a MAC table in this case. So just like a switch, you see a MAC table. There's an aging time written there. So if my addresses are not being, so any forwarding is not happening on those addresses, the MAC address will expire. If the forwarding is happening, it will not expire. And you see the MAC learnings are happening based on the VC label, and you learn the MAC address on. And all the routers will be maintaining the MAC table, just like a bridge. Okay. Any questions at this point of time before Nawaz goes to the pseudo-wire stitching? Because VPLS is a pretty hot technology and many people, yeah, please.
I wanted to use this opportunity to, if there are any ISPs here and have deployed VPLS, I wanted to know, since there are two versions, one over LDP and the other
Yes.
one BGP, I wanted to see if somebody would like to share their experiences with either of them if they have deployed VPLS. The other question I had, if you could talk a little bit about the advantages or disadvantages of both drafts or both using LDP versus BGP. So, thank you.
So first question is, can somebody, if somebody wants to share, if already somebody has deployed VPLS in their network, does anybody want to share any experiences of using different protocols, or how would they? Anybody interested?
Are there any representatives of ISP here?
Yeah.
Any ISPs here? Interesting.
No ISPs.
That's what is
No problem. Regarding the second question, the question is like differences and pros and cons of BGP versus LDP. The only actually, we can take it offline, but I still just want to say, is basically BGP has the advantage of, one of the advantages BGP brings on the table is basically the auto discovery and auto provisioning, which LDP is still, I saw some of the drafts which are talking about the auto discovery and auto provisioning mechanism, but BGP has this inherent there, and BGP can do that. Some of the scaling issues which have been raised in this thing, I'm not sure how much valid are they, but just in case of BGP, I think, or LDP, one of the things is LDP probably can scale well, but probably Nisar can, if you can highlight that thing from your experiences, that is what are the pros and cons you guys have seen there, because most of the people are using LDP in the industry. So that's, I'm just talking about the general, but a lot of things you can do with the BGP at the same time, and the drafts are there which can give the details. I think basically most of the requirement, whatever you want to do, you can use the. Thanks, Nisar. So now Nawaz is going to talk about pseudo-wire stitching, where you have multiple domains and then quality of service. Thanks.
Thanks, Suarez. So folks are lost with VPLS, or why don't we go back to point, make it very simple. Okay. So before talking about pseudo-wire stitching, this is the topology we have been using. Here, one thing which is very obvious is the two P's as we are using in our lab, it's under one AS number, right? But that is not a practical way of doing things. The two P's can belong to different AS numbers, can belong to different service providers. That's a real life example. Right? We showed you a lot of ping and trace route which is working, but both are in the same AS. But in real life we have different service providers. One from San Jose to Dallas. Maybe we might, in this case, I'm showing it as one service provider. But what happens if you have to go through two different AS? All the discussion which we had so far about VPWS, is it holds good? What do we need to do now? So the problem is, there are some drafts defined for this, but let me go over here. We have these two different AS systems, and you have two peering routers or edge routers peering across each other. Now we can have a pseudo wire from here to here and a pseudo wire from here to here, but this is not your attachment circuit. Our attachment circuits are from here all the way to here, crossing across multiple AS. So the solution is there is a draft which is defined to stitch across these pseudo wires. So what do you do here? You create a pseudo wire just like what we have discussed from San Jose PE1 to PE2. And there is another pseudo wire CE2 to PE1 of Dallas. And another from PE1 to Dallas PE1. And stitch at these points. I'm not going to go in detail, but it's more of configuration, provisioning, and there are some control changes. So these are your tunnel stitch points. These two routers. These are your stitch points, as mentioned. Then you have an L2VPN from end to end. So there is a draft defined just to do tunnel stitching. And this is, again, it's transparent to customers. The providers have to make sure they support this feature, and the control plane, and it's more of control plane changes which needs to be done, and that provisioning needs to happen at these points. This is just one example. You can go across multiple, if you have from San Jose to Perth or somewhere in Australia, you have to cross across multiple AS. You will be going through multiple service providers. So all across you have to do this kind of stitch points. Or else the life is simple, you just have one AS, just do a VPWS and everything will look fine. So this is what is called as tunnel stitching, which you do at ASBR. This is your border router. These two. Achieved through interworking of data and control planes at the stitch point. These two stitch points. Nothing happens here. Transparent to customers. It's more of provider's headache. Capability of the boxes which we are using. Okay, that's pretty much about the tunnel stitching part. Now I'm going to talk about more of quality of service. Yesterday we had, in the same room, we had a beautiful discussion on different types of QoS. IP QoS, DHCP, MPLS cost, traffic engineering, a lot of other features, which will enhance your QoS capabilities. But all those were MPLS based or IP based. Now we are going for L2VPN. That means we are using layer 2. Does that mean we are going to lose all those QoS parameters or the efficiency which can be obtained or the QoS kind of the customer which is which requires those kind of QoS, Are we going to lose that? No, the answer is no. We still can maintain, we can still provide based on layer 2 fields the same kind of QoS, or at least close to that. So let's look at some of the objectives of QoS. Provide a level of QoS required by transported traffic. For example, frame relay. If you just have a frame relay network, or if you just have an Ethernet network, or an ATM, you have your own type of QoS defined. You want to maintain that QoS end to end. Or at least at the other end, you want to carry these values. You want to provide different type of service in the code. Or else it will be lost. It doesn't make sense, right? The next one is providing continuity of QoS signals across L2 network. Some of the bits which we have talked about, backend bits, those are valuable congestion parameters. We don't want to lose those values when we send it across the pseudo-wire tunnel. We have to make sure that those bits, as per the requirement of the customer, are given a required QoS. Next one is enforce L2 traffic contract at service boundary. So between user and operator, pretty much it's between CE and PE. The provider might want to define a specific QoS. I don't want to take too much of traffic. I might want to limit this attachment circuit to this rate. Those kind of knobs needs to be done, and that is again defined in the L2 or layer 2 services. So you need to give the flexibility to the customers. At the same time, you want to have control as a provider, how much you are giving flexibility to the customers. Next one is do not compromise on backbone scalability. What does that mean? Just because I'm doing frame relay, Ethernet or ATM, all my P routers and PE routers, do they need to understand each and every single thing? Do they need to maintain these kind of state tables, QoS parameters? It will become more messy and it will be difficult. We have to have a simple method of doing it. Or mapping EXP values, IP values, and the QoS parameters available in these L2 headers. We need to have some kind of mechanism, and it should be simple and scalable. So the final one is fit in broad approach for multi-service core QoS. What does that mean? It is more of, if you have an L3VPN core, we don't need to have specifically designed L2VPN core. Just because we are doing frame relay to any to any, no. The same core should be able to do both L2 and L3VPN. As I said, the PE router, even though it is doing L2 on one sub-interface, it can do L3 services on the other sub-interface. So it has to fit at the broader approach. What are the SLAs which we define in customer, the provider provides, these are the SLAs for these different customers. What are the things which we need to carefully look into? The delay, the variation, the loss of traffic for different pseudo wires, for different attachment circuits. Maybe Ethernet attachment circuit, we have different VLANs. One VLAN might be paying high, so we might need to give them the best QoS for them, or quality of service for them. The other VLANs might not be paying more money to the providers, so you might not want to provide a high bandwidth in the core. So you need to have that kind of control. So the next point says, how do we do that? Marking, policing, queuing and shaping. I'm not going to go and discuss in detail about each of these which has been discussed yesterday, but these are pretty much L3 kind of QoS parameters. Marking, we mark the packets, we color them based on who's red, silver, bronze, gold, that kind of QoS levels, SLAs. Then we police them, we queue them according to, is it based on low latency? Does the customer needs a low latency queuing? Does it need, is he okay with, if it's a voice traffic, do you want to make sure it goes through the, minimum latency? Those kind of things. At the same time, we have to have shaping as well, just like L3. We have to buffer it and we have to shape it. So all the L3 kind of QoS we have to do here as well in order to attain VPWS end-to-end QoS. In QoS for L2VPN, this is a simple diagram. I'm not showing too much of information here. You can see each VC can have similar or different QoS values. It doesn't mean, for example, if I have 5 VCs, all should belong to the same QoS parameters. Each one, each single VC, each single pseudo wire, you can define the QoS. You can define what you want to do. You can define different police levels, different shape levels, different markings based on what they need. Depends on the application they are using. So each VC can be different. How does a service provider prioritize traffic? Because in yesterday we have seen that based on the L3 IPv4 header, using the TOS bytes and those kind of values, DHCP, we use those bits to mark it in our MPLS, EXP. But here, how do we do that? Because we have a layer 2 header. We have a layer 2 packet which is coming towards the PE. And the PE router needs to look at the layer 2 header as well to do that. If you remember, for ATM and frame relay, in control word, we carried these bits, CLP, discard eligibility bits. So based on the control words, looking at the control word, we can mark the EXP value based on these bits. So you can have a mapping of CLP to EXP, DE to EXP. And in Ethernet you have the P bits. Based on that you can mark different QoS values for different MPLS, because the PE router is going to impose the labels, and that is the point where you want to mark, because the entire core is going to switch the traffic or swap the traffic based on these labels or EXP values. So you have an option. You have these values. We have not lost it, right? Because we have used it in the control word. And this is what yesterday we have seen. Based on the IP TOS bits, you mapped it to EXP field. Let's look at an example how it can happen for an Ethernet header. So here you have a customer edge router. He is sending a layer 3 packet with some DHCP set to 5. Once it reaches the CE router, it encapsulates with the Ethernet frame. And it sets the value of P bit to 5 or whatever it wants to, the customer. Now the provider has to take this, read this P bit value. In case of Ethernet it is P bit. In case of frame relay it is DE bit, which is there in the control word. Based on the P bit, it marks the MPLS labels which are imposed at the ingress router. So you have a control of sending traffic from the customer edge as well as marking. You are able to achieve that. Now once it is here, it's the same discussion as what we had yesterday. In the service provider you can have the pipe mode, short pipe mode, uniform mode, all kinds of modes is possible there. So this is pretty much, you have the classification marking coming towards your PE router. You mark it with different colors based on what is the EXP or based on P bits. You queue it based at the PE router or on the PE router depending on how you want to do, and you can shape it at the egress PE router. So there's no demo here, but I'm just going to show you how, for a specific configuration, how it is done. So again, this is more of customer edge router. Under the pseudo wire, we can add a service policy, EXP1. Here what we are doing is we are setting the EXP value to 1. We are controlling at the provider edge router, depending on what kind of attachment circuit it is, depending on who is the customer. It's not just layer 3, it's more of, even in layer 2, we have the control, whom to prioritize, what kind of marking, what kind of QoS we need to provide, what kind of policing we need to provide. Yesterday we had one more discussion on MPLS traffic engineering. Now since we have seen that the pseudowire takes any path, but we want in layer 3 of, we have traffic engineering. We can make use of the traffic engineering capabilities. What was discussed yesterday? How is that possible? For example, if we don't define traffic engineering, let's say you have 2 TE tunnels. Your pseudowire can take any of these two tunnels or an MPLS path available depending on how it is configured. But now you have a knob, or you can provision a specific attachment circuit to one of these tunnels. And this feature is called tunnel selection, where you can select the tunnel the pseudowire can go through. For example, this pseudowire tunnel might be the most expensive one. You might want to give all your customers who are at the edge the TE1 tunnel. And maybe you want to use TE2 tunnel for all L3 services, depending on how you want to do that. So there is a knob available for mapping the attachment circuits to the pseudowires using the tunnel selection feature. So you can define which tunnel you want. If there are n number of tunnels, you can specify which tunnel you want. So that is defined. It's just more of a provisioning. You just have to define which tunnel you want your pseudowire to go through. With that, we have this L2 service transported over a tunnel. So whatever the SLAs which we have defined for TE1, we can make use of that for the pseudowire as well. So we are able to provide all the QoS, MPLS QoS, IP QoS, everything, even in L2 networks. Before I move on to the last topic of today's presentation, are there any questions related to quality of service? So everyone is going to go and deploy QoS? Okay, pseudowire OEM is more of a management function where you, like ping, we just verify to check the IP path. These are some of the tools. LSP ping, just to define, just to verify the LSP path for that particular prefix. Now there is new management, MPLS embedded management tool defined called VCCV, which is Virtual Circuit Connection Verification. It uses the same kind of packet as LSP ping, but it verifies whether your pseudowire is up or not. It's, you ping from PE1 all the way to PE2. The packet doesn't go to your CE, but just stops at PE2, but verifies whether your pseudowire is up or not. Every single pseudowire you can verify using this command. The way you do it is, you just define the loopback address and the VC ID which you have defined. You might have defined tens and hundreds of pseudowires, but one of your pseudowire might not be up, or some problem. Maybe you are using tunnel selection feature, or something is wrong. You can verify whether it's working or not using this specific. It's just an extension of LSP ping. A lot of people would have used it. So it's just using this specific CLI, you can verify the pseudowires. So that's all for L2VPN. But before I go and open the session for Q&A, I got a few comments from during the break session. Some of the people had some questions. One of the question was, I'm just going to use this figure. For any VPWS service, do we really need to have a core? For example, CPE1 might be one customer and CPE3 might be a different customer. But I'm not going through the core, right? You don't need to go through the core. They might be attached to the same PE router, but maybe at different ends. Does this work? Yes, it works. This is called local switching. You send that, your pseudo wire, your attachment circuit AC1 is here, and the second AC is here, and the pseudo wire is stopped. The configuration or provisioning is different, but it is possible. So you can, just like you can have a pseudo wire tunnel from CP1 to CP2, you can have a pseudo wire tunnel from CP1 to CP3, both in IP and MPLS, whatever it is. It's more of local switching. That's the terminology people use it. And one more was more of the convergence related issues. So in the service provider, we haven't had, probably just because of time constraint, we didn't add the slides. A lot of high availability features are still available in L2VPN, which we haven't gone in detail. Like for example, FRR can be enabled in the core to improve your convergence. Just because you are going through the pseudo wire tunnel or through an MPLS core, you can, but just by using this FRR, which converges in less than 50 milliseconds, you can use those kind of things which are available in MPLS and create your pseudo wire. So you don't need to really worry about, okay, it's such a big core, my convergence will be lost. It's better to go with directly connection using a pipe or something else. You can still use the MPLS features available in these cores. So a lot of whatever the MPLS capabilities, the knobs which are available still can be used. Just the way I showed it for QoS, it is possible to use all these features. With that, I open for any Q&A here.
Just to add this, FRR means fast reroute. So that's the terminology we use acronym. So in MPLS world, we have a link protection with a link protection or node protection mechanism where you can basically protect your links, as Namaz has mentioned, and we have it as a FRR. So just for that. So any questions on the floor, or if somebody wants to have a discussion also, that would be good. Or somebody have any questions from point to point, multi-point. No questions. So I assume that everybody has either understood very well or it doesn't make any sense. Anyways, thanks a lot, guys, for your time. And if anybody has any particular questions or have design discussion, Syed Nawaz and I are available right after tutorial. You can feel free to ping us and talk to us if you want to discuss it. Thank you very much.